Okay, hi everyone. I'm Judith, and I want to give you an overview of UnfoldSim, our EEG simulation toolbox. But first of all, I want to take one step back and talk about why to simulate EEG data in the first place. So popular use cases are to do power analysis, to test preprocessing and analysis pipelines, or to validate statistical methods. And of course, if you need example data for an EEG workshop. Because as Bena said, all of you have already implicitly worked with simulated data, and all of this was done with UnfoldSim. But it was all implicit, so now I want to give you a more explicit overview. And so the key features of UnfoldSim are that it's based on regression ERPs that are combined in either continuous or epoch data. And yeah, you also already experienced this feature that you can have overlapping signals, which is really nice to be closer to real data. Moreover, you can also have multi-subject and multi-channel data. And we tried to make UnfoldSim as modular as possible so that the user can choose between existing simulation ingredients, as we call them, or just implement their own to fit it to their needs. To give you a better overview, like how a simulation really looks like, if it's not hidden in a simulation function, is that I will walk you through a simple example where I explain all the simulation ingredients. So the first ingredient is the experimental design. So in this case, we have again the example of bikes versus faces. And there's also a continuous predictor, which could be contrast level, which could either be low or high. And if you specify it in UnfoldSim, you can do this like with different designs. So here it's a single subject design, and you specify a dict with all the experimental factors that you want to manipulate. To get a better view, you can also output the event table. So each row in this event table corresponds to one event. For example, here a face was shown with this contrast level of 1.5. Okay, so there are many more rows. It's just an overview. Okay, having this ingredient, we also need event basis functions. So we need to know what should happen once an event occurs. And there are a few pre-implemented event basis functions which resemble like typical EEG components, for example, a PEV100 or 170, sorry. But you can also then combine them to have more complex signals. And for this example, I chose to have a complex between 3 different components. And of course, you don't want to take them as they are, but you want to combine them with the design. And for this, you can use regression formulas. For example, here, I decided that the N170 should be modulated by image category, such that the response is more negative for faces than for bikes. Then, yeah, having all these components, as the next step, we need an inter-onset distance distribution, or in other words, we need to decide how far in time the events should be apart. And I think we already had a lot of discussions about this. This was called, I think, min overlap before, but it's actually just like the lower and upper bound of the distribution that decides how many samples should be in between. So this is now like I chose a uniform distribution with a lower bound of 100 and also like another 100. So it's between 100 and 200. Okay, so this is like the distribution, but there could also be others, for example, log normal distribution. Like having all these ingredients, the last one is missing, which is the noise specification. In this case, I chose pink noise. And I also plotted it here so that you can see how it looks like. And in the end, like this will be added to the signal. Okay, having all the ingredients, we just mix them together using this simulate function. And that's like what we get out of it, so the resulting data. On the x-axis is time and samples, and on the y-axis is the amplitude. And these colored bars are the event onset, like for the different events, so faces and bikes. And to give you an example how it looks like if I modify certain parameters, I arbitrarily picked 2. So this is the minimal event offset. If I put it higher, then there will be more space between events. Or if I put it to a small range, there will be less space and a lot more overlap. One other thing, for example, is the noise level. If I put it up, then it will get noisier. And also if I put it to 0, maybe that's interesting, then you can actually see like how this is composed of this single ERPs that are then combined. And also here, you can clearly see that there is some overlap. So this was just a simple example, but if this made you curious, I recommend you to check out the documentation or read our JOSS paper. And also we are not done yet, so there are lots of upcoming new features that still have to be merged. So thanks. So I'm happy to take questions.
How would you define a new event basis function? Could you do that based on existing data, for instance, or from scratch? For example, a C1 response.
So you can either like just supply a vector as the event basis function, or you can also define it as a function. So you can actually then also just define your own function. Just let me go back. So here, instead of like a P100, you could also supply a vector or like define your own function. So I have like, I don't know. A bit more. This should work. Yeah, it's a very short one. I think that's like the first one. It's like it's just small step function, like going, from 1 to 10. So it's not that exciting, but in principle, you could, define your function there. I should have made it a bit longer. So my function is just, I think, 6 samples long now.